Hello, and welcome to another edition of Teradata TechBytes. My name is Alexander Golovos, and I am an analytic architect from Teradata's product development organization. Today, we're going to talk about how Teradata's Vantage platform supports the Python language for data science and analytics. This is the third of a 5-part TechBytes series on this topic, which will provide you with an in-depth demonstration of Teradata's Python package, Teradataml. My co-host for the series is Tim Miller, a member of Teradata's Technology and Innovation Office. My colleague, Pankaj Vinod Purandare, is in Teradata's product development department as well, and he assisted significantly in the preparation of the present TechBytes demo. First, let's talk about the assumptions being made regarding the content of this TechByte, as well as the key takeaways we hope all listeners will walk away with. The only assumption is that you have watched the first part of this TechBytes series, which gives an overview of all the R and Python capabilities in Teradata Vantage. Key takeaways from this TechByte include how to use the Teradata SQL driver for Python to connect to a Vantage system, how to use teradataml to wrangle your data directly in Vantage, how to use teradataml to call multiple machine learning algorithms in Vantage, and how to use teradataml to save and manage models in Vantage. To review, teradataml falls into the second user experience, where the language interpreters and packages are running outside of Vantage on a separately attached client or server. Additionally, Teradata's Python package teradataml is also installed on the same client or server machine. The teradataml package provides in-database analytics via Python interfaces to Vantage analytic functions that automatically generate SQL in the backend to call Vantage NewSQL, machine learning, or graph engine analytic functions. And within Python, teradataml provides SQL alchemy functionality. Among the pros, teradataml provides Python interfaces to parallel scalable Vantage analytics. The SQL is generated for you. And teradataml provides an easier path to operationalization. Among the cons, there is a limited number at this time of analytics functions as compared to open source add-on packages with analytical functionality that one could use in Python, and debugging may be slightly more complex when using teradataml. We will examine Python running in Teradata Vantage client systems now. We're introducing the Teradata Python package teradataml. This is a freely available Python add-on library for Vantage. It provides a SQL backend to connect and push SQL to Teradata Vantage. teradataml enables you to use your favorite Python IDE to access Vantage. Integrated development environments such as Jupyter Notebooks, Jupyter Lab, Jupyter Hub, and PyCharm and others are all welcome as a playground where you can use teradataml. With teradataml, user codes in Python. By using teradataml interfaces, one works in conjunction with Teradata SQL driver for Python. The context functions provide database management interfaces. Teradataml exposes hundreds of Vantage machine learning and thousands of NewSQL engine functions as Python interfaces. And teradataml follows Pandas data frame and SQL alchemy conventions. Specifically, teradataml uses the Teradata data frame, which is an object that mimics a Pandas data frame. teradataml supports SQL alchemy methods, aggregates, and operators. And finally, teradataml supports table-to-data frame conversion and vice versa via a few specific functions. Namely, the toSQL function creates a table in the SQL engine based on a teradataml data frame. The copy-to-SQL function creates a table in the SQL engine based on a teradataml or Pandas data frame. And the toPandas function creates a Pandas data frame from a Teradata data frame. Results are stored in Vantage as temporary tables, whereas the user also has the ability to make them persistent tables as well. Following this overview, we proceed to a teradataml demo. Specifically, this TechBytes demo utilizes a use case which builds a model of a fictitious bank to predict the propensity of a financial services customer base to open a credit card account. Various features will be generated by joining and aggregating from 3 base tables, the customers table, the accounts table, and the transactions table, into an analytic dataset. By doing this, we will examine various features that you can use with the teradataml package, which will be done using the Pandas and SQL alchemy features, as well as raw SQL, in order to perform a series of tasks as shown in this slide. Specifically, we will pull through a customer identifier along with demographic variables from the customer table. We will create a gender indicator variable from gender in the customer table. We will create a series of additional indicator variables that will be useful for our analysis, as shown in the next points. We will create average transaction amounts by taking the mean of the principal and interest amounts in the transactions table. And we will also create a quarterly transaction counts by taking the count of transaction identifiers in the transactions table. Following these transformations and wrangling, we will then apply an XGBoost model and a decision forest model. We will build them in the Vantage system on a 60% of the analytic dataset sample. We'll use both models to score the remaining 40% of the data in the analytic dataset. Then we will use a decision forest evaluator to determine the most pertinent of the variables. We will execute a confusion matrix on both scored datasets. And finally, we will show how to save models so they can be reused and scored again in the future. For the teradataml demo, we will use Jupyter Notebook. I am on a client machine on a laptop where I'm essentially about to launch Jupyter Notebook. And as you see, soon after, it is launched on my machine. And now I am actually located in the directory where I have the Jupyter Notebook with the teradataml example. And this is what we're doing here. I'm launching the demo notebook on the browser. Now, in the interest of saving time, I have already pre-executed all the different statements, the Python statements. So I will be explaining how the demo proceeds and will be showing you the results and what to expect. First of all, we need to load the packages that we will be using for our demo. You see that in addition to teradataml, we use matplotlib, pandas, and numpy in our demo. You also see that SQL Alchemy is being used. However, SQL Alchemy is a dependency for teradataml. So when you actually fetch the teradataml package from the PyPy repository, automatically SQL Alchemy and a couple more dependencies are also installed. In the next step, you see that there's a definition of a couple of functions. One is the drawbox plot, which essentially does exactly that. It is a plotting function to draw a box plot. We simply use this code here so that we do not have to repeat this code at a later stage. And we also have a process column to replace null with zero function. This is just a convenience utility that we see here. It's basically a one-liner so that essentially if we encounter a null value within a data frame, then we replace the value with 0. So the first step in our demo is the connection. First thing that you would like to do is to establish a connection to a Teradata Vantage server. For this purpose, we use the create context function, the teradataml create context function, which in the background uses the Teradata SQL driver for Python. And you see that I've already specified a Vantage system, new SQL engine node here as the first argument, the host, and provided a username and password. In the next step, after the context is established, it is important to note that Teradata SQL Python driver at this point, as of July 2019, misses a feature of specifying a default database other than the username. For that reason, if I would like to access tables or objects that exist in a different database, I explicitly need to do so as you see in the following statement. So for example, you see 3 statements following where I'm essentially bringing into the teradataml environment the tables that I would like to use, the input tables in the new SQL engine of my Vantage system, which are the customer table, the accounts table, and the transactions table. So you see that I use the data frame function in teradataml to define a Teradata data frame by specifying now not just the name of the table, but because it resides in a different database, the TDVDB database, I use the in-schema function inside the data frame function. As a result, essentially what I get to do is that I create a link to the actual database table. So there is no actual data transfer of the entire data set that makes the customer table. Instead, there is basically just a small amount of data, a sample of data that is brought over to the client machine. By means of the head function, I can inspect now the TD customer data frame that mirrors the customer table that actually resides in Vantage. Similarly, I also create a TD accounts Teradata data frame that reflects the information in the accounts table on the Vantage system. Finally, I create the TD transactions data frame with information about the customer transaction where you see that for each account number, there are specifics regarding transactions that took place on specific dates, times, and so forth. So I have my initial data sets. The next thing I would like to do is some initial exploratory data analysis. What better way to do this by creating some plots? You see here a series of plots that can help me explore basically features of my data and how the information is connected and some initial insight that I can get. The first plot is a histogram of the income. So you see, for example, here, the plot that is produced by the above code, where the horizontal axis shows the income level, and you see on the vertical the number of occurrences of each bracket of income that is shown on the horizontal axis. You see that's a pretty skewed distribution of income over the count of occurrences of income. The following plot is a bar plot showing the number of customers gender-wise. You see that there's a nearly balanced distribution of male and female customers. Then follows a bar plot with the number of customers state-wise. So based on the state where the customers open their accounts in, you get to see a bar plot that shows how many customers are in which state. So there are clearly some states that have the majority of the customers for this bank, according to the data that we have. Another bar plot shows the number of customers against their marital status. So the marital status here has been assigned a parameter for married, divorced, and so forth. And we also see the number of customers on the vertical axis. And finally, we have a scatter plot that essentially illustrates the starting versus the ending balance of customers. Interesting point here is that this can provide you with insight with respect to potential outliers, that is data points that you might consider as something expected or natural to happen or not, in which case you can actually revise your dataset. Past this initial exploratory analysis, we proceed now with data pre-processing. Here is the part where we proceed to wrangle with the initial datasets that we have and perform the tasks as we saw earlier in the demo overview slide. So first, we would like to, as we say here, grab the customer demographic variables and create some indicator variables for specific features, namely for gender, marital status, and state code. Specifically for the state code, based on the distribution of customers versus state that we saw earlier, we consider a classification of the customers into the top 6 states, and the 7th class will include the customers from all other states jointly. To do so, initially, we assemble the list of columns that will be projected in SQL. For this reason, we use the SQL Alchemy objects column and case, and we provide with this statement essentially the columns that we would like to create and store them in this variable. This is the column projection list that contains SQL Alchemy expressions. And in the bottom, what we essentially do is that we construct the SQL from the list and use that SQL to create a data frame that has the information that was produced by the statement, the earlier statement that we saw before. By doing so and executing it, what we get is now the head of the wrangled customer dataset that now has the newly specified variables. In the next step, we get the account information that is required for the aggregation that we would like to achieve later. And we also create the indicator variables for the account type. So we mentioned earlier that we would like a variable that will essentially have the sum of the starting and ending balance of an account of a customer, and we call this account balance. In a similar way, we create a column projection with this long statement that you see here. And you see how we create the indicators based on the type of the account that we're using. Eventually, we create the ACCT for account, the ACCT data frame that looks as we see here by using the head method for the data frame. And in a following step, we now perform all the transformations we had in mind for the transactions table. So we need to get the transaction information required for the aggregation of the data that we have in mind. So what we would like to do is to create now a column that will specify the quarter in which a transaction was made. You see that we use the case when function in SQL Alchemy to specify the quarter where a transaction took place by means of simple logic. For example, by checking whether a transaction took place in month 1, 2, or 3, then the transaction is classified under quarter 1 transaction, and so forth. This statement eventually leads to the creation of a data frame from query by using this projection of the for transaction. This data frame looks like this. So after performing tasks on each one of the individual initial input tables, the final task is to bring together the 3 transformed tables into the analytic dataset. Initially, we would like to left join the ACCT and trans data frames into an account underscore trans data frame on the basis of ACCT and BR. We construct a list of all column expressions to be projected, and in this process, we create new columns with transaction amounts as shown in the following. Eventually, we construct a SQL left outer join from the clause statement above by using the join function, and from this join object and the previous projection, we create the ACCT trans data frame. The result is now a new data frame that essentially has the left join of the account and transactions tables. The next step is to perform another left outer join of the account trans frame with the customer data frame on the customer ID column. As you see, now we can use teradataml and the join API to join the 2 data frames, but we also want to process few columns in a way that if a column contains null, then we would like to remove the nulls and replace them with 0. To do so, we use another case object, and this is where the function process column to replace null with 0 comes handy, as defined in the very beginning of this notebook. Eventually, what we have here is another column projection, and this is now the column projection for the join of the account trans data frame with the customer. We then define the join object, and eventually, by using the data frame function, we create the analytic dataset PyJoin, which looks like this. So essentially, here is where we have all of the features, okay, all the different columns that we need to proceed with our analysis from the initial input tables. The only thing that we need to do is finish up our joins with aggregation and rolling things up by the customer ID variable. And essentially we use the ag method, okay, after we group by customer ID to produce the analytic dataset, ADS_pi. By doing so, we would like to persist this data frame, the ADS_pi, into an actual table in the database. Do this by using the copy to SQL function. So we specify that we would like to create a table named ADS_pi from the data frame ADS_pi and replace the object if already exists. As you see in the beginning, we essentially do a try statement where we attempt to drop the table if it already exists, so as to ensure that we might avoid any error if the table is already there. By doing so, what we do is that we create now Teradata data frame based now on the actual table in Vantage, the ADS_pi table in Vantage, that we call TDADS_pi, which looks like this, and this is our analytic dataset. These series of steps complete the first part of our teradataml demo, which deals about wrangling and transformation of your data in Vantage. Alternatively, if you feel more comfortable with SQL code, you could have actually performed all these operations above that you saw with Python code by means of SQL. Python enables you to essentially compose a SQL query, as you see here, We just call all of this text ads_SQL, and then you can execute this query by means of the execute method in the getContext function. As a result, you would have gotten, in an alternative way again, the analytic dataset by means of submitting just pure SQL to be executed in database. The result would have been the exact same analytic dataset. Now, on we go to use our analytic dataset to create training and testing subsets from the persisted table ads_pi. What we would like to do is to split the analytic dataset into a training and a testing data subset. We would like to use 60% of the data in the ads_pi to create our training subset, and the rest 40% will be used for testing and scoring. We do this by means of submitting essentially SQL that uses the sample keyword to do the splitting of a table into percentages as shown here. We submit the SQL by creating a data frame from the query that we specified just above, and this data frame essentially now contains the td_train_test data. That is the 60% of the underscore of the ads_pi analytic dataset that we saw before. Note here that we have added one last column in that dataset, which essentially has the sample ID. The sample ID column has the value 1 if the specific row belongs to the first subset, or the value 2 if the specific row has been assigned by the sample function to the second subset. The only thing that we need to do now is to essentially separate these two subsets, and we do so by creating Teradata data frame, where we essentially take all the rows from the td_train_test data frame with sample ID 1, and that makes the train query, and then we use the remaining 40% of the sample to assign to the test score subset, which we call test query. We are now ready to proceed with the actual analytic operations on our analytic dataset. What we are going to do in the following is that we will essentially model the information that we have with two different approaches. One is an XGBoost algorithm, another one is a random forest algorithm, as we said, to derive from our data the propensity to open a new credit card account for a customer. First, we start with XGBoost. XGBoost stands for Extreme Gradient Boosting. This is an algorithm that is designed and optimized for boosted trees and aims specifically at large-scale tree boosting. What we would like to do is that, assuming what the formula is, we specify first this formula here as a long string so that we can have it handy, and then we would like to train an XGBoost model to predict credit card account ownership on the basis of the above formula. So teradataml has the XGBoost Python function, which is essentially a front end for the corresponding machine learning engine analytic function in Vantage, where you see that we use the specified formula as the prediction formula that we would like to use. The ID column is the customer ID. We perform this operation on the train query data, which is the training subset, and we will be using some characteristics as follows. We have 4 trees that we're using, a binomial loss function, and what we would like to do is a classification analysis. The execution for this specific instance on our system takes about 1 minute, and you see in the standard output information that has to do with the model characteristics per se under the model table output, and there are also a series of messages that have to do with the results that we get back from the model, the actual fitting process. Such information includes, for example, the number of boosting iteration it took for convergence, the number of total trees and subtrees used, and so forth. Having fitted this model, we would now like to score with this model against the 40% data and see what results we actually get. So in this scenario, we use the XGBoost predict function now, where the input is the model that we just fitted. The input data are the test query data, that is the scoring subset. And again, we are using essentially the same number of boosted trees. ID column is the customer ID, and we are interested in comparing our results against the credit card account index. To do so, we get results, and the results we would like to essentially save in a table that we call XGBoost scores. so that we can persist our results as a table in Vantage. From this table, we create a Teradata data frame that we call TDXGBoost scores, and by doing a head 100, we get a sample of 100 lines of these scores. Where essentially now we see for each customer ID the actual credit card account index and the predicted value alongside with the prediction upper and lower confidence intervals. So you see that some of these predictions agree and some of these do not. Okay, like for example here. We will see the quality of our predictions at a later stage after we actually now move on and use a second algorithm by using, for example, specifically random forests, to also go through the same cycle of training a random forest model and then scoring the test data with this model as shown in the following. The Teradata's implementation of random forest is called decision forests. These are ensemble learning methods for classification and regression. They can construct a multitude of decision trees at training time, where decision forests take essentially the mode of the classes for classification tasks as in our example. In regression tasks, decision forests essentially take the prediction values from all individual trees. So we use a classification tree type as shown here. The input data come from the train query, training data subset. The formula is the exact same formula that we also used with the XGBoost model. And we use a maximum depth of 12, whereas at each level we take up to 5 independent variables to use, and the specified levels of seed values are shown below as well. We use a rather high number of trees for our model, and in this case on our system the execution took just a few minutes to run. The result again provides us with information regarding the details, some metadata regarding the model fit. There's also the model output with the results, whether the decision forest was created or not, how long it took for the query. Actually see 144 seconds, which is about 2.5, 3 minutes. And there's also a series of messages following, which actually are pretty similar to what we have above. Now, for the random forest algorithm, we need the decision forest evaluator in Vantage. This is a function to determine the most important variables in the decision forest model. By using 5 levels and taking in as object the newly fitted decision forest model, what one gets is essentially the series of importance for all different trees that were fitted. What we would like to do now is to essentially aggregate these results to obtain summary statistics across all the trees, over grouping by each variable, so that we can see for each variable one measure that will show us the importance of this variable for the specific model. In teradataml, you can see here that after grouping by the variable column, we use the describe method in the very end that essentially provides a summary of statistics across all the trees. By asking to print the result, what we get is essentially 3 columns. The variable column, which is a listing of all the variables, and then the statistical results that are produced by the describe method. There are different numbers that correspond to different statistical measures. For example, one can select the mean of the statistics across all trees to define the importance for the specific variable. Given the sample of the results that we see here, we see that the importance value ranges for different values. We have, for example, for the AZ resident index, value of 0.019. For the California resident index, this variable has a slightly higher importance, equal to 0.053. We see further down that the average balance of the checking account, the CK AVG BAL, is clearly an important variable because we see much higher value of the mean at 0.157. In the same way, what one can do is one essentially could aggregate the few or several variables that have the highest values of the importance parameter, and typically one could use now just these values to run again a fitting of a new model by using, for example, decision forests anew, to simply go for an improved prediction by using the most important of the variables, of all variables that have been used. We're skipping this step in the interest of economy and showing essentially the next part, which is scoring now the test data by using the decision forest model that we just fitted. We use the decision forest predict function That takes as input the model that we would like to use, which is the one that we just fitted and saved in this variable. The input data come from the test query subset of our ADS. The ID column again is the customer ID. And what we get in a similar way is the prediction that we decide to save in a persistent table in Vantage as random forest underscore scores. And by creating a Teradata data frame random forest underscore scores, we can see the results as shown here. So these are the first 100 rows of the random forest underscore scores table, where we see the credit card account index as the second column, and the prediction is in the fourth column, accompanied further right by the lower and upper confidence intervals. Clearly, the next thing that we would like to see is how well each one of our models fares for these classification tasks that we just performed. For this reason, we're using a confusion matrix to look at the two different models, the XGBoost and the decision forest models. We invoke now the confusion matrix teradataml function twice. The first time, we simply use the XGBoost underscore scores data, where we need to simply specify what the prediction variable is and what the reference variable is. The results include the actual confusion matrix as the count table output, where you see essentially that the models fare well. What we have here is essentially if we get to see the true positives and true negatives against the false positives and false negatives, the numbers are quite indicative. And we can also see the results from the perspective also of the statistics table, where we get a similar idea on the basis of the parameters like the null error rate, the kappa value, and so forth. The third table that is provided is the accuracy table, and then we follow up with the same task for the random forest analysis, where essentially we see that the prediction task appears to have been slightly inferior to what we got from the XGBoost algorithm. Now assume that you have the models and you are satisfied with the results and that you would actually like to save them and reuse them. TeradatamL has an experimental feature that enables you to perform model administration. Please note that the model administration APIs that we are showing here are not officially supported as of the teradataml version 16.20.0.0.2, and the actual APIs are not exposed to the end user. However, these will be coming in a future version, and we're presenting those here as an illustration of what you can do with teradataml. So assuming that you like a specific model that you would further like to somehow store, teradataml provides you the opportunity to store the model metadata in the database and retrieve them at a later point. To save them, simply invoke the command save_model by providing the model that you would like to save and by giving it a specific name. By running these commands on both models, you actually receive a validation about the persisted tables that have been created for the models that you would like to save. You get a success message for saving the models. And in the next step, if you would like to actually list all the saved models that you have in a database, by typing list_models, you essentially get a listing. You see the first row is the decision forest model and the second row is the XGBoost model. The information that is also shown is the engine on which the model was built, what class the model is, and also the creation date and time. Now for any specific model, you could use the model's name to get more detailed information from the model metadata. With the describe_model and a specific model name, in this case the decision forest model_1, what you can get is a detailed description of key model metadata for your information. This way, you can know what parameters were used to build this model, other than basic information as we saw before, that is, when this model was created, what class it is, and so forth. If you know that you have a model that you would like to use, the retrieve_model function that takes as argument the name of the model that you would like to use can be used to essentially retrieve it and save it again locally as a parameter under teradataml. And in this way, you can use this model repeatedly for different scoring tasks in subsequent sessions. Finally, if you no longer need a model, you can use the delete_model function with a model name, with the accompanying model name, so that you can actually delete this model metadata from the Vantage cluster. In this example here, we delete the decision forest model 1, and by listing the models, we see that the only remaining model is the XGBoost model _1 that we also saved earlier. Once you're done with your analysis, you can very simply finish the session by using the remove underscore context that essentially removes the context that you created for your initial connection to the Vantage cluster of your preference that we specified in the beginning of this demo. And at this point, you're simply complete and ready to continue with any other task you'd like to perform. With the completion of the teradataml demo, we conclude part 3 of using R and Python with Teradata Vantage, the teradataml demo. This is the end of the present TechByte. Thank you very much for your attention.